Hello, this is KStevMath coming at you with a new math video. This is for the pre-calculus class that I'm doing with Math UC as the curriculum guide. Like, that's the curriculum I'm using is called Math UC. You can check it out by just Googling it if you'd like to. This is going to be lesson 1 of Precalculus Introduction to Trig. And before I forget, if you would like to follow along with this video using a notes page, then go to the website in the description that also should be popping up right now, hopefully, so that you can get that notes page, and that way you won't have to try to draw the triangles yourself. You can just print it out and write all over it and save it for when you're doing your homework later. So we're going to talk today about trig. Perhaps I should have started this slide actually with the title, What is Trig? Because that's what you're going to see a lot. So trig is an abbreviation for trigonometry, because let's face it, trigonometry is a mouthful to say, and the more you try to say it, probably the worse you get. Like, same with precalculus. Earlier, whenever I tried to start the video, I tried to say precalculus and it was just not good. So anytime you see trig, it's short for trigonometry. Human beings, we're lazy, so we like to say as little as possible. So you're probably going to see it referred to as trig quite a bit. But what trigonometry is a branch of mathematics dealing with triangles and the relationships between the sides and angles of those triangles. And it kind of encompasses that essentially, but it can feel like there's so much more to it. Like if you take a class titled trigonometry in high school or in college, then there's a lot of things that go with that, but it all kind of goes back down to triangles. If you have taken geometry, which hopefully you have if you're watching this video, then at some point along the way you guys talked about sine, cosine, and tangent. Those are trigonometric functions, and so anything that deals with those functions is also a part of trigonometry. And you might be thinking, well, wait, I'm here for precalculus. Why are we talking about trigonometry? And so precalculus is just this kind of generic course description that we've come up with that encompasses anything that you haven't already learned that will be helpful for you to know before you take calculus, which is just kind of a weird place to be in some ways. So we will talk about some things that are more algebra based in this course, but here at the beginning we are going to talk a lot about trigonometry, because in calculus you will need to use trigonometry. So this is the branch that we're working with right now. What does that mean? What are we going to do here in this introduction to trigonometry? Well, the first thing we're going to do is we're going to remember some things from geometry. And the very first thing, and all of these are going to have to do with things we learned about triangles. The very first thing probably is something that you'll remember once I've said it. The angles of a triangle have a sum of 180 degrees. That is true for any triangle that's actually a real triangle. So if somebody draws a triangle and labels the angles, and those angles add up to be something other than 180, they've not created a real triangle. So that is something that has to be true about triangles. The three angles add up to be 180. And here at the start of trigonometry, we are going to be focused on a very specific type of triangle called a right triangle. So if you remember from geometry, right angles are 90-degree angles. They're also not wrong angles. See what I did there? Okay, anyway, a right triangle is a triangle that has one right angle. And so that means that the other two angles are going to add up to make the other 90 degrees, if you haven't already thought about it. 90 plus 90 is 180. So if one of our angles is 90 degrees, the other two added together has to also equal 90 degrees. So you may find yourself getting super good at adding things up or subtracting in such a way that you get either the number 90 or 180 as you go through, if you were in geometry, or as you're going through trigonometry here. And the final thing we need to remember from geometry, at least the final thing I remembered in time to put it on this slide, is the Pythagorean theorem. And I actually recently did a whole video to remind you how to use the Pythagorean theorem, link in the description, so check that out if that part of what we're doing you don't feel super familiar with. But if we have a right triangle and we know two of the sides, no matter which two they are, we can use the Pythagorean theorem, a squared plus b squared equals c squared, to find the third side. And so that's something that we should already know from geometry, that we're going to come into this knowing and using almost right away. And another video that I did recently that you might check out before this one, if you haven't already, is about special right triangles. So link in the description for that as well. That's also something that may be helpful for you to know, although it's not quite as important as knowing how to use the Pythagorean theorem for us at this particular moment. So my hope is that this is going to feel fairly easy and fairly, or pretty much like review, because most geometry classes do go over the three main trig functions: sine, cosine, and tangent. So if you going through this are like, wow, this is easy, what am I even doing here? That's great. Stick through, do the examples, try to do them ahead of me to make sure that you remember how to do it, because this is something that we are going to build off of. If you're feeling like it's not easy, then you're in absolutely the right place, because this is something that we really, really need to get before we move on to harder things. So the three main trig functions that we learn about in geometry and that we use all through well, not all through geometry. We use all through trigonometry and precalculus, and then we use a whole bunch in calculus, are sine, cosine, and tangent. And I actually on the screen have those three words written out. And that's because we actually maybe forget sometimes that those are what they're called, because if we're using our calculator or if we're writing them down, we use abbreviations for each of them. Even though sine in particular is not very, very long of a word, for some reason we abbreviate it SIN. So when you read that, you don't read it as sin for a variety of reasons, one of which is who wants to talk about sin when you're in math class, right? But also we look at that and we say, oh, this is talking about the sine function. Or if you see COS, we're talking about the cosine function. And then when we see TAN, we're not talking about how tan you are, we're talking about the tangent function. The other thing on the screen that you may or may not be super familiar with is this thing next to each of our trig functions and in the triangle as well, that is a theta. It's a circle, kind of like a zero, not a circle, it's more like an oval. It looks like an O or a zero, but it has a line through it. And that's the Greek letter theta that, I don't know who decided this, but somewhere in math, people liked using theta as angles and it stuck. And so instead of us having to label our angles in our triangle with things like A, B, X, Y, things that we might, use for other things, we often use theta. And we also are going to see in this lesson the Greek letter alpha as well. And so basically, there's a lot of letters, right, in the English language, but some of them we kind of throw out because they look like different numbers or things like that. So theta is what we often use for representing angles. So what are these trig functions? Trig functions create a relationship between the angle of a triangle, or just angles in general, actually. It doesn't necessarily have to even be in a triangle. It gives us a relationship between angles and a ratio of side lengths. Let's stick with it being related to triangles. Let's not open up a Pandora box here. So saying sine of theta, SIN of theta, you can equate that, you can put that equal to the ratio of the two sides of our triangle that are opposite of the angle and the hypotenuse. So I've got this triangle drawn out. I'm going to use my mouse hopefully to kind of point at things. So I've got theta down here, and so the sides of my right triangle I can label as three different things. The hypotenuse is always the side that's across from the right angle, and so no matter which of these two angles I label theta, the hypotenuse is always the hypotenuse. But the other two sides can switch depending on which angle is labeled. So from theta, which is down here at the bottom right, the adjacent side, think about what the word adjacent means. Adjacent means next to. If you are adjacent to your sibling or adjacent to your parent, you would be next to that person. Whereas, so maybe you're sitting at a table and there's a bench on either side. If you are sitting directly next to somebody, you'd be adjacent to them. Whereas if you have somebody on the other bench, you would be sitting opposite, right? So that's kind of the way we can relate words that we already use in our normal everyday life. You use the word adjacent all the time, right? With how it's working in this triangle. So the adjacent side is the one that is actually the angle is actually sharing that side with the hypotenuse. And then opposite is the one that is all the way on the opposite side of the triangle. And so then we can relate our angle with those sides using these functions. So sine of theta equals the opposite side, whatever it is, over the hypotenuse. Cosine, so over here on the right, is equal to adjacent over hypotenuse. Tangent is opposite over adjacent. So we can label these sides with opposite, adjacent, and hypotenuse. We can label the angle we want to think about it with, and we can come up with these trig values, these trig ratios. And it is a little weird thinking about what this is actually telling us. And so if you're not interested in the why, this is where you can skip ahead and go to the examples. But if you are interested in trying to understand why we even care about sine, cosine, and tangent, I'm going to give it my best go. So what's happening here is we have triangles that are similar to each other. That any right triangle that has a 45-degree angle down here at the bottom, automatically we know would also have to have a 45-degree angle up at the top. And then the side lengths that we have, we may not know what the side lengths of that particular triangle are, but we know that they have to be proportional to every single other triangle that is 45, 45, 90, which is actually a special right triangle, by the way. What that means is that all of a sudden we don't have to know all three sides or even two sides of that triangle to be able to figure out the rest of the sides of the triangle. Because if we know what one of them is, we can figure out the other ones either using sine, cosine, and tangent, or by the fact that for this one I'm talking about a special right triangle. And that's helpful because think about places where there might secretly be triangles. And so we could think about having a building and having a ladder leaning up against it. And so all of a sudden we've got a triangle where the ladder is the hypotenuse. The building hopefully makes a right angle with the ground. And so maybe we know what one of those measures is. Maybe we know how tall the ladder is, right? Because ladders tend to come in certain heights. So maybe it's a 10-foot ladder, and so we're curious about, how far up is it that the ladder is reaching on the building. And so if we know parts of this triangle we've created, we can come up with the other parts. Sine, cosine, and tangent allow us to do this knowing fewer parts than if we were just trying to use the Pythagorean theorem, which needs two of the sides to be known. The other thing that it helps us with is allowing for an angle to play a part, whereas the Pythagorean theorem doesn't talk at all about angles other than the fact that it has to be a right triangle. So maybe it's that we actually know two of the sides of our triangle and we want to figure out what that means the angle is. Or the other way of thinking of it is maybe we know what angle we need. Think about a ramp, like a wheelchair ramp. Those have to have a certain angle or lower. It can't be a 45-degree angle or right with the wheelchair. So they have to have a certain angle or lower. So that gives us an angle to work with. Maybe we know how long this way the ramp needs to be, right? And so it could help us figure out how long do we need the ramp hypotenuse. So there are lots of cool things that we can do with this, and today we're just going to focus on how do I use sine, cosine, and tangent, and then we'll build off of that, and we will end up actually seeing some word problems in real world situations where this could be helpful to us. Almost forgot, there is an acronym that we use to help us remember these, because you may be thinking, how am I supposed to remember which sides go with which trig function? And so I'm going to write it down up here that we tend to use the acronym SO, CA, TOA. And you could come up with, you could make an acronym with this that has each of these letters start a word and maybe makes a sentence, or you could just try to memorize it as these three weird words, right? So, CA, TOA. And that's actually how I have it memorized. And I would love if you can think of a sentence that goes along with this. There are ones out there already that we may or may not like. So I'd love for you to leave a comment if you come up with one yourself, some sort of sentence to help you remember this. And I'm gonna try in my oodles of spare time that I have as a mom and a teacher to also think of one, because I think that we've really sold ourselves short on fun acronyms for SOHCAHTOA. TOA. I honestly just remember the three words, so, ca, and toa, and every time I have to use sine, cosine, and tangent, that is in my head, so that I can use that to remember which sides go with each. So let's look at some examples here. I've got 2 examples that we'll do together, and then I've got a now you try, where I want you, if you haven't already, to pause the video, try it yourself, and see if you've gotten it right. Now you can actually do that at any point along the way here, because it's a video. You're able to pause, rewind, fast forward, slow it down. I was about to say slow it up. You can slow it down if you feel like I'm talking too fast, or you could speed it up if you think I'm talking too slow. But if at some point you're like, I think I have the hang of this, pause the video, try it out yourself, and then play the video so that you can see. Or if you get stuck, you can play the video and get unstuck. Because really math works best whenever you have someone that's kind of able to hold your hand along the way. And it's a little bit difficult to do that as a video, but not impossible. You just have to be more active in the hand holding than you normally would, because you have to be willing to say, okay, I'm gonna pause here, see if I know what to do next. Okay, now I'm stuck. Okay, play. Okay, now what is she gonna tell me what to do next? Yes. Okay, now I'm gonna pause and play, pause and play. Okay, sorry. We don't need to keep going with this. Example 1, we are finding the sine, cosine, and tangent of both theta and, okay, here's that other Greek letter I told you about, alpha, and express the ratios in fraction form. So what it's asking us to do, because, man, sometimes the directions on our math homework is the worst part of the whole thing, figuring out what they're asking us to do. So we are going to figure out what is sine of theta, what is cosine of theta, and do not write out the whole word here. We want to use these abbreviations because that's what they're there for. That's the whole point, is so that we don't have to write as much. So we want to find sine, cosine, and tangent of theta, and we also want to find sine, cosine, and tangent of alpha. And my alphas are going to look a lot like a fish, because I haven't ever actually tried to make them look like anything else. And I don't know, do you think that alpha looks like a fish like I do? Like this little fish? I don't know. But that's what mine are going to look like, so we'll just deal with it. So as I'm doing this, I'm thinking about my acronym SOHCAHTOA. And I'm going to do these separately. So as I'm thinking about theta, I can label my sides. The hypotenuse is going to be the same no matter what, and I'm going to abbreviate on this as well. The hypotenuse is 2 squared root of 13, because the hypotenuse is what's across from the right angle. But these other 2 sides, 4 and 6, we're going to label with adjacent and opposite. So 6 is this side here that is next to theta, so 6 is our adjacent side. And 4 is opposite of theta. And if you're struggling with labeling these as opposite or adjacent, just take a moment and really try to figure out, okay, why would this one be the opposite side and not the other? Keep in mind that it's from the perspective of theta, so just completely ignore, maybe cover up the alpha. Okay, from the perspective of theta, think about it like you're standing where theta is. You're inside a triangle. What side is adjacent to you and what side is opposite? Which of these, if you pretend that you're in this triangular room at theta, which wall could you theoretically reach out and touch? That's your adjacent side. You also have a wall you can touch, which is your hypotenuse, but the hypotenuse is special because it's across from your right angle. And then what's the wall you can't touch? That's the wall that is opposite to you. That's the first time I've ever tried to explain it that way, so let me know if that helped or not. Now, sine comes from putting the opposite side over the hypotenuse. So from theta, the opposite side is 4, and the hypotenuse is 2 square roots of 13. Now this is our answer in fraction form, but it's not in the best fraction form that we could come up with. For one thing, 4 over 2 is something that simplifies. And the rule for simplifying when square roots are involved is that things outside of square roots can simplify and things that are both inside can simplify, but you can't like cross simplify. So if there was an even number underneath our square root, it wouldn't matter. We wouldn't simplify the 4 or the 2 with the inside of our square root. They only simplify with each other. So right off the bat here, I can actually cancel out a 2 from this 4 and this 2. But the other thing that we normally do with fractions like this in math that have a square root on bottom is we rationalize them. And so rationalizing a square root means take the square root and times it by itself so that you move the square root from the bottom up to the top. And this is like kind of a math grammar thing, that it's really kind of a personal preference for mathematicians, or a way that we can all come up more easily with the same answer than if we don't consider rationalizing as a best practice. We're going to go ahead and rationalize things just so that we are have the practice of being more mathematically correct. So on the bottom, square root of 13 times square root of 13 times 1, right, because I cancel out the 2. Well, square root of 13 times square root of 13 is 13. Because if you do multiply them together, you get 169, and the square root of 169 goes back to being 13. On top, we've got 2, and we've got the square root of 13, which together make 2 square roots of 13. And that's our answer. The square root of 13 and the regular 13 don't cancel out. They don't interact at all because one's inside the square root and one's outside the square root. So that would be our ratio for sine theta, 2 square roots of 13 over 13. So now let's look at cosine of theta. So now we think cosine, cosine adjacent hypotenuse. So I'm going to take the adjacent side 6 and put it over the hypotenuse 2 square roots of 13. I'm going to go through the same process where I simplify the 6 and the 2. They're both divisible by 2. And then I times the top and the bottom by square root of 13 to move the square root of 13 from the bottom to the top. So on top now I have 3 and square root of 13, and on bottom I've got just 13 because I've got 1 times square root of 13 times square root of 13, which is just 13. Let's look at tangent, TOA. So tangent equals opposite over adjacent. It does matter which one you put on top and which one you put on bottom, as we will see in the very next lesson, because if you don't already know that flipping a fraction over doesn't make it the same exact fraction, this is a good time to learn that. If I flip it over and do adjacent on top and opposite on bottom, I'm not talking about the same fraction as opposite over adjacent, unless they were both 1, and then it would actually be the same. But how often does that happen, right? Probably not super often. Tangent of theta is the opposite over the adjacent, so we're going to put the 4 over here on top of 6 and then simplify. And rejoice a little bit perhaps because there's not a square root in this one at all. 4 over 6 simplifies to be 2 over 3. You can see I box, that's the best looking box of the bunch. I box my answers so that if somebody's looking at this, they can see hopefully pretty quickly where the answers are. It is good to show work and to have that step in between where you've written down the initial thing before you simplified. That way anyone looking at it can, if you've made a mistake, can hopefully help you find where that mistake was. But it is also nice to box the answer so that somebody can see that more easily. Now let's do this from the perspective of alpha. So I don't need to erase where I labeled it as a hypotenuse because that is still going to be my hypotenuse. But what I do now that I'm thinking about alpha is I have to switch the opposite and adjacent sides. So now picture yourself in this triangular room standing at alpha. Now 4 is what's adjacent to you and 6 is what's opposite to you. Okay? And now we're going to do the same thing with sine, cosine, and tangent. So sine is opposite over hypotenuse. So that's 6 over 2 square roots of 13. Now wait a second. I feel like we've simplified 6 over 2 square roots of 13, don't you? We simplified that back here when we did cosine of theta. So we can go through the steps and simplify it again, or we can say, well, I'm pretty sure I simplified it right. So this should just equal 3 square roots of 13 over 13. Well, let's look at cosine. So cosine is adjacent over hypotenuse, so 4 over 2 square roots of 13. And so now we're going to look, wait a second, we've simplified that before already too. That's what we got when we did sine. So that's 2 square roots of 13 over 13. And now let's do tangent, opposite over adjacent, TOA, 6 over 4. We did not simplify that, but we simplified something pretty close to it. We divide them both by 2 and get 3/2. There is no need, by the way, to change improper fractions to mixed numbers unless you are going to use that fraction for something and you're thinking, oh, it'd be really nice to have a mixed number here. But for the most part, there's not usually a reason for us to change it. It's just a personal preference. So here's my answers to the sine, cosine, and tangent of theta, sine, cosine, and tangent of alpha. I'd like to perhaps spoil something for you or perhaps lead you to discover something. Do you think that it was a coincidence here that our alpha sine and cosine are the same as our theta sine and cosine but flipped? Do you think that's a coincidence, or do you think that's something that will happen every single time? Let's make sure to look at that on our next example to see. Example 2. Find the sine, cosine, and tangent. Oh, this is the same thing we just did, so I guess I don't really need to say all of it again. Okay, so we're going to look for where theta is. It's up here at the top of our triangle. So I can label my sides with hypotenuse, adjacent, and opposite. And remember that our acronym is SO, CA, TOA. And so then we want to figure out what sine of theta is. Opposite over hypotenuse. So from theta, the opposite side is 8 over the hypotenuse, 8 square roots of 2. 8 over 8 square roots of 2. Those 8s are going to cancel out so that we have 1 on top and 1 square root of 2 on bottom. And then we'll rationalize this by timesing by the square root of 2 on top and bottom. So on top we have 1 times the square root of 2, which is just square root of 2. And on the bottom we have 1 times square root of 2 times square root of 2, which is just 2. So sine theta is square root of 2 over 2. Let's look at cosine of theta. So now we've got the adjacent side over the hypotenuse, which is 8 over 8 square roots of 2. Ooh, this is the same thing that we just did. So it's going to be actually not necessarily conclusive for us to wonder about what happened on example 1 with sine and cosine for theta and alpha, because our sine and cosine here actually should end up being the same. This should also simplify to be square root of 2 over 2. Interesting. And let's look at tangent. So opposite over adjacent is 8 over 8, which cancels so that we get 1 over 1, which is simply 1. Interesting. Now let's look at sine, cosine, and tangent of alpha. If you haven't already realized, by the way, this is looking a lot like a special right triangle. Like, I actually know what these angles are because of my familiarity with special right triangles. And if you think about it long enough, you might know as well. And if you don't recognize this as a special right triangle, that's a sign that maybe you should go and watch my video on special right triangles. So again, the link is in the description. Check that out. And then, come back to this and say, oh, now I know how you knew. Now let's look at sine, cosine, and tangent of alpha. Sine of alpha. So opposite over hypotenuse. And I relabeled these as I was talking. So 8 over 8 square roots of 2, which again simplifies to be square root of 2 over 2. And then cosine of alpha equals adjacent over hypotenuse, 8 over 8 square roots of 2, which again simplifies to be square root of 2 over 2. And then tangent of alpha equals opposite over adjacent is 8 over 8, which again simplifies to be 1. So this was kind of an interesting and weird situation because of it being a special right triangle and having the two legs be the exact same like that. So let's look at our now you try and see if we've got the hang of this. This one is a little different, mainly in that the square root is one of the legs instead of the hypotenuse, which can throw you off. Any little difference in an example can throw you off whenever you're trying to do it on your own. But I do want you to try to do this on your own and see if you have the hang of it. And if not, if you get stuck, well, simply watch the video up until the point you were stuck and then watch a little further. Hopefully you'll figure out where you went wrong, and then you'll be able to do the rest of the problem on your own. So let's start with sine, cosine, and tangent of theta. Let's label our sides. Pause it, by the way, if you haven't already, so that you can try it yourself. So our opposite side is 5, our hypotenuse is 10, and our adjacent side is 5 square roots of 3. Remember, our acronym is SO, CA, TOA. And so our opposite side 5 and our hypotenuse 10 go together, 5 over 10, and we simplify that. We always simplify our fractions to the smallest numbers possible, just out of the kindness of our hearts, and because, I mean, it's like it makes it more right. It's still right that it's 5 over 10, but it's more right to say that it's 1/2. So our answer here is 1/2 for sine. Now let's look at cosine. So adjacent over hypotenuse is 5 square roots of 3 over 10. Now, because our square root is not our hypotenuse, this is actually making it, at least so far, a little bit easier than our other ones were, because the square root of 3 is on top, not on bottom, which means that I do need to simplify the 5 over 10, but the square root of 3, I'm not going to rationalize that. I only rationalize when the square root's on the bottom. So 5 and 10 simplify to be 1/2, which means that this gives us square root of 3 over 2. Let's look at tangent. And so here we're going to do opposite over adjacent. So 5 over 5 square roots of 3. Now this one we do have to rationalize. So the 5's cancel and give us 1 over 1. The square root of 3 we're going to times by on top and bottom. So that on top we have 1 times the square root of 3, which is square root of 3. On bottom we have 1 times square root of 3 times square root of 3, which just gives us 3. So here's our sine, cosine, and tangent values for theta. Let's look at our sine, cosine, and tangent values for alpha. If you were stuck and you've watched the video to get unstuck, and then you could pause it again, by the way, so that you can, try more on your own. Also, by the way, we are trying to, we're hoping to see if that connection we made in example 1 between the sine and cosine of our two angles maybe possibly always being flipped of each other. We do want to check to see if that is something that happens here, since our sides are different, our legs are different. So sine of alpha, okay, we need to switch the opposite and adjacent side. So now this one's opposite and this one is adjacent. So sine of alpha is, I want opposite over hypotenuse. 5 square roots of 3 over 10, which simplifies the 5 and the 10 to 1/2. So that's square root of 3 over 2, which is the same as what we got for cosine of theta. So far that thing that we thought might be happening on example 1 looks like it might be happening here too. Cosine of alpha is adjacent over hypotenuse, which is 5 over 10, which simplifies to be 1/2. Okay, so it happened to us again here, that these are just flipped of each other. And also, by the way, tangent, which is going to be 5 square roots of 3 over 5. It's a little bit harder to tell because of rationalizing, but I get the square root of 3, which is actually the reciprocal of the other one that we got, the tangent of theta. It's a little harder to see. It'd be easier if we had left it as 1 over the square root of 3 and then think about flipping it over. That gives us just a regular square root of 3. So if we don't usually actually do this in triangles where we find the sine, cosine, and tangent, all 3 of them for both angles, partially because we don't need to. Sine of this angle should be the same as cosine of this angle, and vice versa. And then tangent, of the two angles are reciprocals of each other. So that's not actually something we normally do as we're working through problems after kind of this intro lesson, because once we've gotten the hang of finding them, then we just use whichever trig function seems like it'll work the best. So you look at what do I know and what does that mean I should use for a trig function. So just throwing that out there. So how'd it go? Did it go well or did it not go so well? If it didn't go well, you're welcome to comment and maybe I can help out with that. And if it did go well, go ahead and comment and I'll give you a thumbs up because I am so glad to hear that it went well. Thanks for watching. I have a website, KStevMath.com, that I upload resources on all the time, and I'm trying to make that website grow and grow so that basically you could someday go through any math course you want on that website with resources and videos and all sorts of fun things. So definitely check that out if you'd like to. The other thing that would really help me out is if you would give this video a thumbs up and if you'd subscribe if you haven't already. If you are interested in taking pre-calculus with me, I'm doing this class using the Math UC curriculum, which you can find online, and I'm doing it with a local to me homeschool co-op, but there is an option to do it online with me. You don't actually have to be where I'm from. You don't even have to know where I'm from. But if you'd like to do that, there is a link in the description for that so that you can follow along with that. And I hope to see you in the next video, which should be out pretty soon. Thanks so much.